Okay, the shaft shown is supported by 2 bearings and it's subjected to 3 torques. Determine the stress developed at point A and point B located in section AA. So here's our section AA right here. And so we have point A and point B. Point B is at 0.15 inch radius. So we're looking for an internal stress. Point A is at 3/4 of an inch. So it'll be the outside, the maximum stress. So as we look at this, what do we know? Well, we're going to assume we're in a linear elastic region and our stress is going to be equal to T rho over J, where rho is our diameter of where we're locating the stress. So how do we look at this? We do it the exact same way that we would do an axial stress problem. We have to solve the statics to find out what the internal torque is in the shaft. Because once again, just like with our shafts, we always wanted the internal force. Well, right now we need the internal torque. So how do we solve that? We go back to mechanics and we sum up all of our torques. And our torques have to be 0. And we'll say, I like using counterclockwise as positive. And it really doesn't matter which way that we look at this, because we're going to end up getting the same thing no matter which way we go. So if we look at it from this direction, free body diagram of the shaft is we have the shaft, and then we have, one torque here, we have torque 2 here, we have torque 3 here. It's in a couple bearings, so it'll freely rotate, so there's nothing holding it on there. And so if I cut it right here at AA, what do I need? Well, I need an internal torque that balances everything out to keep it moving. So in this case, I have 12.5 kip inches going in the positive direction. Well, to balance that out, I would need 12.5 kip inches in the negative direction. So what if we do it the other way? Well, let's find out what's going on there. Well, if I take a look at this one, I've got 42.5 kip inches going in the positive direction. I've got 30 kip inches going in the negative direction. Well, to have that balance out, then I've got to have 12.5 kip inches in the negative direction to balance things out. So it doesn't matter which way that we approach it, we're going to end up with the same thing regardless. So now what we need to do is let's start solving that equation. So shear stress is equal to T rho over J. Now the torque's going to be the same no matter which point that we look at, because it's the internal torque across the area. So we do now have our torque, 12.5 kip inches. So 12,500 pounds times inch. So now what we have is rho, or rho's given to us in the problem. So now we have to look up the polar moment of inertia. So if I go into my textbook, or if I go into my engineering equation manual, I'll find that the polar moment of inertia for a circle is pi over 2 radius to the 4th. Now, polar moment of inertia for both these points is going to be the same, because the polar moment of inertia is an area property. It has nothing to do with the points that we're looking at. So if I look at that, my outside radius is 3/4 of an inch. So I'll plug in 0.75 inches, raise that to the 4th. And what we will have for a polar moment of inertia is 0.497 inches to the 4th. So at this point, we have everything we need. Let's calculate out the shear stress. So I have the shear stress in point A, torque, 12.5 kip inches, kip times inch. Rho is the radius that it's at. This one, A, is the outside radius. This is going to be our maximum shear stress, 0.75 inches. And then we're going to divide that by J, 0.497 inches to the 4th. And if I take a look at 2 of those inches will cancel out. I'm going to be left with kips per inches squared, or KSI, which is a unit of stress, so I should expect that. So at point A, I'll bash that into my calculator, end up with 18.9 KSI. So there's the amount of shear stress I have on the outside surface of my shaft. The only thing that changes for point B is going to be where we're located. So 12.5 kip inches times, now that radius that I'm dealing with is, I'm at 0.15 inches because I'm looking at the stresses on the inside of the shaft. Everything else is the same. The polar moment of inertia is an area property. The torque is an internal torque. It's not going to change. Once again, I end up with kips per inch squared. But if I bash this out, 3.77 KSI at point B. So as we look at it, we can see there's quite a bit of increase as we go across there, because we're going from a little bit less than 4 to a little bit less than 19 over the space of that shaft. And so as you know, we've got that linear relationship as it goes from point A to point B.